Hi students, this is your lesson 6.10 and it will be covering the instantaneous rate of change. So this is where you're going to estimate the slope of a tangent line to a function at a certain input given the equation. So I'm going to start you with the equation and we'll be able to go from there. So a couple of definitions, I'd like you to make sure that you pause and copy these down into your notes. A tangent line, you may recall, is a straight line that intersects a curve at one point, such that the slope of the line is equal to the slope of the curve at that point. So we can see here at point P, we have this tangent line, and it's touching only right here at P, which is the point of tangency. Now further on, it intersects the curve. We're just talking about the tangent at that point P. And of course, if we have point Q, we could try to draw a tangent line here. Again, it would just touch right at that one point of tangency. The instantaneous rate of change of a function is the slope of that tangent line. So if we have a line, we know that we can do the average rate of change. So we're going to use what we did last lesson with just reviewing our average rate of change, and we're going to apply it to this instantaneous rate of change and our tangent line. So here's our first example. What is the instantaneous rate of change of this function? So given this equation, f of x equals negative 5x squared plus 12x plus 2, and we want to talk about this at the input of x equals 1, and then we actually want to write the equation of the tangent line. Let's take a look here. If you can go ahead and go to this Desmos calculator. I'll go ahead and post these slides so that you can access that. Obviously, if you're watching the video, you can't, but this is what it's going to look like. And we'll get into the actual calculations in a moment. But if you go to this link, there's a slider. Mrs. Schulten set this up, I did not. And this slider, you can move this point wherever you want. And wherever you move it, it's going to draw a line that intersects with the point 1, 9. Now remember, we talked about that input of 1. So we could very well take these 2 points and calculate the rate of change. This is our secant line. This is what we did last class. We could move that closer and now look at what our secant line looks like. We could calculate the average rate of change again. And we can get closer and closer and closer until we're right at this 1 point and we have that tangent line. Now we know if we have a tangent line, we have a single point that we know, we can't calculate the slope with a single point. What we can do is try to calculate all these little secant line slopes from both directions. And the closer I get, the closer we should be to what that slope is. And I'm going to show you this with some calculations. So let's go back here to this equation. Okay, we're going to set up a nice organized table for this. So this will be our inputs. This will be the average rate of change between the point 1 comma something, we'll fill that in, and x, y. Okay, now first of all, we need to find out where is that point. And we were able to see when we looked at the graph, it's 1, 9. But let's say we didn't have that graph. We would go ahead and just say, okay, what is f of 1? So it'd be 1 squared plus 12 times 1 plus 2. We would do those calculations and get 9. So we want the average rate of change between this point 1, 9 and some xy point. Okay. So remember, we're trying to converge or get very close to this input here of 1. So let's get very close from both sides. Let's start here with 0.9. That's pretty close to 1. Then we're going to get even closer, 0.99. Then we're going to get super close, 0.999. Okay. Now from the other direction, so this is coming in from the left. From the other direction, the closest, if we kind of mirror this, 1.001, 1.001, and 1.01. All of these are very close to 1, and hopefully we're going to see that these get closer and closer to what looks like the same value, the same average rate of change. So let's remember we do our slope, and we always do our change in y over change in x, nothing new there. So we would say, okay, f of x minus, in this case, we want f of 1 over, and then we would say, for this one, x minus 1. Okay, let's fill in what we know. F of x, we know, is right here. So let's write that in. Negative 5x squared plus 12x plus 2. And then minus, what's f of 1? It's 9. And that's all over x minus 1. And I'm going to clean it up just one more little bit here at the end. Oops, I forgot the x. Plus 12x minus 7 then, x minus 1. So this is our little formula, which is just our average rate of change, nothing fancy here. And what we're going to do is we are going to plug in all these different inputs. And we're going to see what happens. Now, notice you can't plug in 1. What happens when we plug 1 in here? We divide by 0, that's undefined. So we're not allowed to do that. So what we need to do is look for some pattern to lead us to what the slope is of that tangent line. Okay, so if we start with, I'm going to write down one of the examples. You're going to do this on your paper. Obviously, please pause me, try this out. Let's look at the 0.9. So let's do that first. So I'm going to write negative 5 times 0.9 squared plus 12 times 0.9 minus 7 all over 0.9 minus 1. I'm going to type this whole mess in my calculator, and let's see what we get. Okay, so after I type all this in, 2.5 is the average rate of change. Okay, so what I did, just to kind of give you a visual of what is happening here, if I go back to my graph, I'm looking at 0.9. So I'm coming in from the left. This would be 0.5, 0.75, so somewhere pretty close. And what I just did is I found the slope of this secant line, which is 2.5. Okay, so, excuse me, that's what we're looking at. And then we're going to get closer. Now, 0.99, that's going to be really close. And we're going to see, well, what's that slope of that secant line? And then 0.999, we're going to be right on top of that point. Okay, I would love you to go ahead and pause this, and I'd love you to fill out the rest of these little highlighted portions, leaving the middle blank. Okay, so hopefully you were able to find these values, and you should see that you're getting really close to 2. If you look from both directions, and I'll fill out the rest of these here, 1.95, we can see as we're going closer and closer from the left and the right, we have a value of 2.005 and 1.9995. That looks like we are converging upon the slope of 2. And so this is actually the slope of the tangent line, which we're going to call the instantaneous rate of change. All right, now the next part is actually finding an equation for this tangent line. So if we want an equation for this tangent line, we are thinking y equals m, and we're going to do this with our hk. with our horizontal and vertical shift. So the slope in this case is 2. That's what we just calculated. And the only point we know for the tangent line is 1, 9. That's it. We only have a single point. So y equals 2 times x minus 1 in parentheses plus 9. And if you want to go further and put that in slope-intercept form, that's totally fine. I'm going to leave it in this HK form. Okay, now, here is our next example. And this will be the second and last example we do together in the video. So we're going to do the same type of thing as we just did. We'll practice this with a different function. And this one is actually on page 32, the first problem in your packet. So you can actually write right on the packet. So again, we have a point 1, 0.5, and it lies on this curve. Use the table to find, or use a table to find the slope of the tangent line at point P. Here's point P. And then write the equation of the tangent line. So this time they gave us that full point P. So let's go ahead and make our table. And I want you to be real organized here, labeling what we're doing. So this is the average rate of change between the point of tangency, 1, 0.5, and some other xy. Okay. In the middle is always what we're trying to head to, right? So here we're going to write, we're trying to look at as we get closer and closer to 1 from the left and the right. Now, in this case, we're going to use the same values as we did on the last one because we're still looking at this value of 1. That won't always be the case, but we'll just kind of be consistent and use this again. Okay, and then 1.0001. And again, we're just trying to get real close to prove what this instantaneous rate of change would be. So we look at a little formula here, change in y over change in x, which we know. And so we'll say, okay, so it's f of x minus f of 1, right, over x minus 1. All right, well, what is f of x? That's x over 1 plus x. That's right here. Okay, and it's y equals actually. And then minus, well, if I plug 1 in, what do we get? We would get 1 over 1 plus 1, which is 1/2, which is exactly what we had right here. Okay, and then over x minus 1. So what we can do now is we can plug in our values. So the first value we can plug in here is 0.9. You would put the 0.9 everywhere you see an x and go ahead and calculate. Okay, so take a moment, fill out that table. Okay, so I'm going to go ahead and show you the values that we get. And hopefully, again, you're seeing it's getting closer and closer to what looks like the same value. And we could even get closer and closer. So we could obviously keep going. We're going to call this good enough. So again, we're looking from here, and what are we getting closer to? 0.25012 and 0.24998. That looks like we're really close to 0.25. Okay, so this is the slope of the tangent line. Which is our instantaneous rate of change. Okay, remember when you have these pictures, you have a graph with one point on it, and I'm saying, hey, find the slope of the line that goes through that one point. You don't have enough information. You need 2 points. So what we do is we pick pairs of points that are getting closer and closer, and then we're going to hopefully converge upon that same value. Here's a little heads up. If you don't get really close to the same value, there's a mistake somewhere. Okay, it should always converge to the same value, but that could be a computation issue. So for the equation, again, I have x minus h and then plus k on the outside here. So we can go ahead and put in our values. The point we are using is 1 comma 0.5, and our slope that we just found is 0.25. X minus 1 plus 0.5. And that is the equation of the tangent line. Okay, definitely sit with this, write down your questions, be ready to go in class, and let's ask whatever questions you have, and we will get those answered.